Thanks for watching AI Weekly Update from Henry AI Labs. This is a weekly series going through miscellaneous blog posts, published papers, and news in the space of machine learning and AI. The first article this week is Google's Mina chatbot. This is a remarkable chatbot resulting from training a 2.5 billion parameter evolved transformer model on 40 billion words of social media conversations. This results in amazing inference such as inventing a joke in a conversation, this horses go to Haver joke. Next we'll look at this incredible blog post on curriculums and reinforcement learning. This is the idea of trying to figure out the best order to present data to a model or the ordering of tasks robots should perform in order to learn more complex skills. Then we'll go through another great blog post on contrastive self-supervised learning, different papers using loss functions between positive and negative samples to form representations. Contrastive learning is based on the intuition that we only keep representations of objects for the sake of distinguishing them from other objects. Then we'll look at Facebook's Polygames platform, open sourcing a framework for doing zero learning, this kind of Monte Carlo tree search enhanced with neural network policy and value functions used in AlphaGo 0, Alpha 0, and Mu 0. Then we'll look at encode, tag, and realize, a new way of doing sequence encoding decoding for text generation that focuses on assigning these tags to words rather than generating the words themselves. Then we'll look at this paper from Microsoft researchers, ImageBERT, which is a really interesting way of fusing text and image features to do tasks like text-to-image retrieval, image captioning like MS Coco, and these other tasks of joint text and image features. Also from Microsoft Research, we'll look at this blog post on explainable machine learning through diverse counterfactuals, looking at ways to perturb the inputs to see what kind of inputs would produce predictions of the opposite class that it had originally predicted. Then from Google's blog, we'll look at this post on detecting hidden signs of anemia from the eye, looking at different characteristics of their paper, like improving their detection from 74% to 88% on this area under the curve metric, and looking at other characteristics of the paper, like this kind of an attribution visualization. Then we'll go through this example of doing hyperparameter tuning with the Keras Tuner API from the TensorFlow blog. We'll also look at the high-plot, high-dimensional interactive visualization with these parallel plots from Facebook's AI blog. We'll also look at this announcement of the third workshop and challenge on learned image compression at the CVPR 2020 conference from Google's AI blog. OpenAI's announcement of switching their stack to PyTorch, also updating their spinning up and deep reinforcement learning tutorial, and other things relating to their switch to PyTorch. We'll also look at this blog post from Covariant AI, describing their launch and the challenges with respect to bringing AI robots into these warehouses and doing these kind of sorting tasks and miscellaneous things like looking through transparent bottles with their 3D cameras. And then finally, we'll look at this blog post from FloydHub on describing tokenizers, how machines read. This week, one of the most exciting events in artificial intelligence research has come out, which is Google's Mina chatbot. This chatbot is largely the result of a dataset on social media conversations of about 40 billion words that takes up about 341 gigabytes and is modeled by a transformer model with 2.6 billion parameters. For the sake of reference, the GPT-2 model that came out with OpenAI's stage release had about 1.5 billion parameters in the largest model compared to 2.6 billion in the Mina chatbot. NVIDIA has trained a larger model known as Megatron LM with 8.3 billion parameters, describing model parallelism and this idea of exploring how you can chunk different parts of the model across different accelerators to train these enormous transformers. Mina is most famous for this horses go to Haver joke shown here, which really demonstrates how amazing the model is because this kind of a pun isn't in the data set, meaning that in the language modeling task used to train Mina, it never sees something like Haver before, go to Haver, the character level combination of hay and verd, or anything like that would make this kind of unremarkable and almost like memorizing the data set. So really what's happened is Mina has seen so much data and is such a complex model that it's able to understand this kind of wordplay from other examples. And it's probably also worth noting that the byte pair encoding tokenization scheme, which later in this weekly update, I'll recommend a new tokenization article, blog post that was published on FloydHub, but this kind of tokenization scheme probably also has a lot to do with this kind of an inference capability as well. Google has also published a really great paper describing their Mina chatbot system as well, discussing things like how they evaluate chatbots with their sensibleness and specificness metric. So sensibleness describes this idea that the chatbot's response makes sense at all, and then specificness gets the chatbot out of doing things like I don't know or okay, which are sensible answers but not specific and useful as a chatbot. So specificness is whether it gives you an answer like I love tennis compared to a more specific answer like I love watching Roger Federer play or something like that. So in the paper they discuss a lot of this about human evaluation of chatbots, also things like the difference between static and interactive evaluation of chatbots, comparing how you judge a chatbot when you're just reading a transcript of it, of its already recorded conversation compared to talking with it yourself. And the paper also discusses interesting things like when you tell the human evaluator that they're taking a Turing test and how that biases the way they interact with the chatbot. They also describe the application of their evolved transformer architecture, which is the product of large-scale evolution, neural architecture search, and it's interesting how they show this correlation between test perplexity, which is this common evaluation automated metric for language modeling, and their sensibleness and specificness metric for evaluating chatbots. So it's a really great paper describing this system. I'd also like to thank Bianca A. There's Art to Data Science for this comment on my video on this paper towards a human-like chatbot. This comment really helped me understand how this kind of a chatbot would come up with something like horses go to Haver. She gives this example of how there could be examples in the data set like who's making that monstrous buzzing noise, and then a beast, having this kind of a wordplay with the two E's being a bee and also a beast, like a monstrous kind of thing. So it's a really great example that really helped me understand this kind of idea of how this Mina chatbot might be able to infer something like Havered from the data set by other examples of wordplay like this. This week, Lillian Wang posted a really great article on curriculum learning for reinforcement learning on her blog. The blog post begins by explaining curriculum learning. Curriculum learning is this idea of having an order to the way that the data is presented to a learning model, compared to just randomly sampling data points from the data set as is usually done in stochastic gradient descent training. The first anecdote motivates this idea of curriculum learning. You wouldn't teach a 3-year-old how to integrate if they don't even know how to do basic addition or multiplication. So the idea here is similar. We're trying to build these curriculums to order the data or order the tasks that the robots have to learn or different reinforcement learning agents as they learn more complex skills. The blog post goes on to describe curriculum learning methods into 4 general paradigms. These paradigms are teacher-student, self-play, goal generation, and skills extraction. Teacher-student describes the most general and well-known case of curriculum learning, where you have a teacher which is looking for a way to order the data or the task to present to the student network, and then you have the student network trying to learn from that data. A common example of this would be the case of image classification for CFAR 10, where the teacher network is looking to organize mini batches to present to the image classifier compared to just sampling randomly, and the score would be the accuracy from the student network back to the teacher. Self-play is the next paradigm describing the case where the teacher network has some knowledge of the task itself. So in the first paradigm of teacher-student, the teacher network doesn't actually know anything about the real task itself. It just has its action space of the task to select to present to the student network or the order to present data, compared to self-play where Agent Alice in this case is actually experiencing the environment as well and is using that to inform its presentation of tasks to Agent Bob or the student network in this kind of an idea. An analogy here would be, say, the difference between like a coach and a player, and this being like a basketball coach and this being a basketball player, and this being more of an example of like a varsity player and a junior varsity player, where the varsity player is advising the junior varsity player how to improve their skill based on their actual knowledge of being in their shoes previously, compared to the coach who maybe doesn't really have the same experience as the player, maybe some kind of analogy like that. But anyway, so the self-play curriculum is used in reinforcement learning for things like maze navigation, where Agent Alice will traverse the maze, and then based on their experience, the agent's experience traversing the maze, will propose intermediate points or like positions in the maze that Agent Bob should try to get to learn more about how to solve the maze. The next 2 paradigms are a bit more complicated, such as goal generation, which adapts the generative adversarial network framework to have this generator that's proposing a goal, and then discriminator that's trying to say if the goal is reasonable or feasible or not. Then the next idea is skills extraction, which is another ambitious idea, trying to extract the skills from the agent and then use this to form the curriculum for future learning. So these 4 paradigms make up the framing of the article to describe different types of curriculum learning and reinforcement learning. Now we'll go through this blog post explaining some of the miscellaneous ideas presented in the blog post. The first is task-specific curriculum, looking at different papers that are looking at ways in which to order the data points presented to the classifier. This is a really interesting paper that is cited in the blog post titled On the Power of Curriculum Learning in Training Deep Networks, a paper that I've made a video on. It's a really interesting paper exploring 2 general ideas, pacing and scoring. So scoring in their paper describes using a pre-trained classifier to rank the difficulty of different training points in an image classification problem based on the confidence or like how uncertain the model is with the prediction. So say the difference between something where it predicts 90% dog and then like low percentages for the other classes compared to where it predicts say 40% dog, 20% cat, some distribution like that where it's more uncertain. So use that kind of a notion to score different data points, and then it explores different ways of pacing functions or different ways to organize the data points once you've already determined the respective difficulty of each of them. This is a really interesting paper exploring curriculum learning that does find a lot of advantages to doing this kind of a curriculum compared to just random sampling from the data set. The next interesting paper cited in the blog post is learning to execute. So this is a really interesting paper. In the paper, they describe how curriculum learning really helps them train these models. These are really interesting models. It's a paper that I hadn't known about myself. It's kind of a sequence where it takes in as input this Python program, and then the output is the result that would happen from running this code. So I thought this is a really interesting paper that I'm excited to look at later. And then the blog post describes the use of task-specific curriculum in automatic domain randomization. So this OpenAI Rubik's Cube hand, what they do is they generate a curriculum by having the distribution of environments, like the different parameters of the physics environment and the vision models, changing over time as the model is trained. So then the blog post goes on to describe the teacher-guided curriculum, cases where you treat the curriculum like an n-arm bandit problem, really highlighting this idea of the teacher having no real knowledge of the task itself, rather it's just kind of pulling levers, like in the n-arm bandit problem analogy, to try to find the ways in which to order the data presented to the student. Then describes teacher-student curriculum learning, similar to the neural architecture search paper with reinforcement learning, where the teacher is the controller and the student is these child networks, sending the feedback and then sending the new model architectures. So similar kind of paradigm used for curriculum learning as well. Other things like adapting this to continuous task spaces and miscellaneous other things on teacher-student. Then it goes on to curriculum through self-play, describing this paper asymmetric self-play, where you have this maze navigation task. Agent Alice navigates the maze and then proposes places that Bob should try to go to. And then automatic goal generation, the idea of using a goal GAN where you have the generator and the discriminator, formulating the intermediate goals or the task curriculum in order to do this kind of a curriculum learning technique. Then you have this paradigm of skill-based curriculum, which is really interesting, but maybe a little more complicated, where you have this latent space that determines the skills, and you use the latent space of the model parameters in order to organize the data, and it's a meta-train, and definitely a paper that I'm excited to look at, but haven't looked at yet, so wouldn't talk too much about it. But yes, this is definitely a really interesting blog post, curriculum learning for reinforcement learning. I highly recommend checking this out. Researchers from Microsoft have published a really interesting paper titled ImageBERT for combining text and visual embeddings into this kind of a BERT-like architecture. And they do this to achieve state-of-the-art results on these kind of text-image multimodal tasks like the MS COCO object detection and Flickr 30K. So they describe their architecture of combining, well, first they describe how they collect this data set and how they filter it by taking the web image text pairs and then filtering it through things like dominant image detection and these kind of classifiers in order to process the data. So once they get these data samples of things like this image and then the corresponding text pair, a golfer sitting at the edge of sand trap, head and hands, and this kind of other images compared to things that have been parsed away from the pipeline that they describe in this stage of the paper. So then once they have these text image pairs, they put them into this model, the ImageBERT. So it's a complex model, but basically what they do is they're doing 4 tasks at the same time. They have, are the image and text related or not? They have this some kind of feature regression based on the bounding box thing, as well as doing the object classification of the thing in the bounding box. And then they have the masked language modeling task as well. So it takes in the image embeddings. So these image embeddings come from the faster RCNN, the region of interest proposals, is how this is filtered into the embedding of the sequence. That comes as well as the text sequence. So you see how this is has the text pair, an old man swimming in a pool. This text sequence goes into the BERT as well. And then it has these embeddings like the sequence position as well as the segment embedding. So like the image and then the text and then the ordering of the tokens. So then it performs all these tasks at once. So definitely a complex model, but really interesting to see this kind of a model that's trying to handle text and vision information at the same time. I came across a really great article on contrastive self-supervised learning from Ankesh Anand while scrolling through Hacker News. This blog post describes different algorithms for contrastive learning, which is well described in this example of drawing a dollar bill from memory. This analogy highlights problems with generative models that reconstruct data in the pixel space and then uses the intermediate representations of the generative model for tasks like image classification. Probably the most famous example of this would be the big BIGAN model. But this isn't how we would model something like this. For example, we can't reconstruct a dollar bill in the pixel space unless we have a dollar right in front of us to use to draw the dollar bill. But our dollar bill from memory would look more like something like this. So the idea of this paradigm of contrastive self-supervised learning is that representations of objects are primarily based on distinguishing them from one another. And this is the idea of the algorithms presented in this blog post for doing contrastive learning. The blog post describes this general paradigm for thinking about contrastive methods. The idea here is that you have some function where you're trying to extract some representation of the image and you want it to be similar to parts of the positive sample and different from the negative sample. So look at the 4 different papers presented in this blog post as an example of this contrastive learning framework. The first of which is Deep Info Max. So in this case, you have this global feature that's extracted from the entire feature map of this dog image, and then you want it to be as similar to local features on this dog image as well, but different from the negative images or the negative local features on this like Jaguar image. So this is the first example of contrastive learning, where you can see that you're trying to take this difference between positive and negative samples. So the next paper presented is probably one of the most popular or successful papers on data efficient ImageNet classification, is the contrastive predictive coding, and the second version of this paper that came out. So the idea here is that you have more of a sequential structure to the way that you order the encoding of the positive and then the randomly sampled negative sequences. So back to that framework, you would want these global features from the whole entire sequence to be as similar to the next one in the sequence that's masked for the sake of encoding this, and you'd want them to be as different as possible from the negatively sampled token. The next paper is learning invariances with contrastive learning. It's kind of like this idea of consistency regularization, like unsupervised data augmentation, or the top half of a fixed match, where you want the classification of the image where it's after it's augmented with some kind of augmentation like a translation or a color space thing to be similar to the original image compared to negative samples. The next idea is this momentum contrast. So the momentum contrast is a really interesting idea for overcoming memory bottlenecks of this idea. So this is the first idea of contrastive loss, where you have this end-to-end, where you have a loss on the encoder of the positive sample as well as the encoder of the negative sample. So the contrastive loss is a way of getting away from having to store this memory for the encoding of the negative sample, and instead looking at this momentum encoder for the negative sample in a different way of having gradients flow through this kind of contrastive learning task. So it's a really interesting article. All these papers are really interesting, and they're definitely some complex techniques, but really worth looking into. From Google's AI blog is Encode, Tag, and Realize, a controllable and efficient approach for text generation, and also the corresponding paper describing in more details this algorithm. So the idea here is that instead of having the encoder and decoder, where the decoder is doing the language modeling and generating text in the sequence-to-sequence kind of task, where you might take like some sentence like this as input and then generate another sentence as output, rather the idea behind this laser tagger is to tag each word based on these actions of like keep, delete, add a phrase, and this kind of idea. So it parses this input sequence, and the output sequence is the tagging of the different words that are parsed to turn into the new sentence for doing different things like text editing and like maybe like grammar checking, I don't know, things like this. But the idea is that you delete different words in order to form the new sentences. So it's a way they describe in the paper how some of the advantages of doing the laser tagger compared to the traditional sequence-to-sequence language modeling task. So they describe that this gives you control. The inference speed, probably 100 times faster, is obviously a huge advantage with something like this. And then it's more data efficient, which is also good as well. So it's definitely an interesting paper, something that I'm excited to look more into. And you can see this plot showing that it's useful for this case where you have this setting of training examples, and you want to get something with faster inference is always good as well. Microsoft's research blog is published about an open source library providing explanations for machine learning through diverse counterfactuals. The idea of counterfactuals is an approach to explainable machine learning that looks at perturbing an input such that it produces a prediction of the opposite class to help you get a better sense of why it might have predicted this for the given input. So you see when this input is mapped to increasing income by 10,000 would result in getting approved for the bank loan. You get a sense of what features are modeling this, but obviously with these deep neural networks and things like this, it can be a really complex interaction between features, making these kind of counterfactuals difficult, and it's also difficult to make them diverse. So having a diverse set of features that change to get different points on the decision boundary. So they also offer an interesting example of this with the with predicting the I think income, and then having these different features, and then suggesting changes to the features that would result in a different prediction for the adult income data set. So I think it's an interesting idea, the counterfactual explainable machine learning, especially I think with things like the AI job screenings, where they might take in like your resume as input and then either pass you on for an interview or not. I think it'd be interesting if they had these counterfactuals that could help you suggest things to improve your resume to make it past the AI job screener when you get rejected. It's definitely an interesting library, and you can also check out their paper on this, Explainable Machine Learning Classifiers through Diverse Counterfactual Explanations. Facebook's AI blog is also posted about HiPlot, high-dimensional interactive plots made easy. So what this is this kind of a data visualization where you have this parallel plots that's frequently used for hyperparameter optimization. You've probably seen this kind of a plot before with the weights and biases visualization of these different hyperparameters. So this is another library for doing the same kind of visualization made by Facebook. So basically what you have is these different values for the dropout, learning rate, the choice of optimizer, and the loss. Then you have these routings between the values used and then the final result. So you see this routing of 0.3 for dropout, 1e-1 for learning rate using the Atom optimizer. That led to a higher loss than this other route did. So that's kind of the idea of visualizing these plots by using these parallel plots. So it's definitely an interesting kind of way of visualizing this. It describes some more ways of making this interactive and making it so it's more tractable to visualize this for yourself and understand what you're looking at by having this interactive component as well with the HiPlot library. And they describe some other things like how they use this for their population-based or evolution-based search strategies. So definitely an interesting library, open source visualization with respect to things like AutoML and hyperparameter tuning. Google's AI blog has announced the third workshop and challenge on learned image compression at the upcoming CVPR 2020 conference. This is the idea of compressing an image dataset to 0.15 bits per pixels while evaluated with image quality metrics like peak signal noise ratio and I think something like multi-scale structural similarity image metrics, something like that. But there's different ways of evaluating how well the image is reconstructed after it's compressed, and these kind of things are used for things like JPEG and these other image encoding techniques. So it's interesting to see more about this compression challenge at CVPR, workshop and challenge on learned image compression. Definitely an interesting idea. Also was motivated by this to check out this blog post from Heartbeat, Fritz AI, a 2019 guide to deep learning based image compression. This is a really great article that has like a long list of different papers to check out if you're interested in getting a sense of learned image compression. It's definitely something I haven't really gotten into myself, but it looks really interesting. And I think this is the paper to start with if you want to check it out. Variable rate image compression with recurrent neural networks. Facebook's AI blog is published about open sourcing polygames, a new framework for training AI bots through self-play. So this is an open source library, a framework around training models on different board games for this idea of zero learning. So you can see the GitHub repository for polygames if you'd like to check this out for yourself. It's based on this idea of zero learning. So zero learning describes this idea from the AlphaGo Zero, where you have this kind of combination of Monte Carlo tree search with these deep neural networks for policy and for policy selection, the mapping of state to actions, as well as value networks for predicting the expected reward from a given state, and then combining the neural network estimators in Monte Carlo tree search. So this kind of paradigm is what's described as zero learning. So in the framework, they present a lot of different ways. In the paper, they give a quick overview of this idea of zero learning, combining Monte Carlo tree search with neural policies. And then in the paper, they describe some of the features of this open source framework. So things like, having the models already, having like a net-to-net kind of way of adjusting the model. So one thing, they have this script to convert that makes the growth of the neural network easy. So they say you want to add more residual blocks. And I also think it's worth noting that in this paper from OpenAI, Dota 2 with large-scale deep reinforcement learning, a key contributor to this is that they do this net-to-net. So basically, when they want to use a bigger neural network, they don't just throw away the one that they've been training for, say, 4 months. They have this way of doing a function transformation into the bigger model that preserves what it's been doing for the last 4 months. So I think that's another really interesting part of this framework, as well as things like tournament mode to fight catastrophic forgetting and avoid oscillating performance. So it's definitely an interesting framework, this polygames for improved zero learning. Google's AI health blog has published a really interesting article on detecting hidden signs of anemia from the eye. So there's been a lot of research from Google, also a Kaggle competition, I think, on doing this kind of diabetes prediction from these retinal images. And now they're showing how they can do anemia detection as well, citing that the deep learning model improves the detection from 74 to 88%. So this is an example of the images that they're looking at. It's a non-invasive eye image that from this they can get a lot of information. I don't remember exactly where I saw this from, but they can do things like predict the age and gender from these images as well. These surprising things they're able to get out of these kinds of images with these deep learning models that are trained on enormous data sets. So they also show in the picture of the blog post this kind of an attribution technique, showing which part of the original image contributes the most to the final prediction of the model. Interesting visualization. And you can read this article, Detection of Anemia from Retinal Fundus Images via Deep Learning. It's published in Nature, but you can get past the paywall by clicking on the link in the blog post. If you're interested in this kind of thing of doing this prediction from these fundal images, I highly recommend watching this keynote from Jeff Dean, where he discusses some of the work they're doing with this. And it's a really great keynote describing a lot of other things about machine learning and AI. Another interesting update to AI this week is OpenAI's announcement of standardizing their deep learning framework in the PyTorch library. So moving over to PyTorch, including more examples of PyTorch and the spinning up and deep-RL tutorial series, as well as developing these block sparse kernels in PyTorch. So these block sparse kernels, this idea of taking advantage of sparse neural networks, which is a really hot thing in deep learning right now. Well, always has been, but definitely more and more popular with things like lottery ticket hypothesis, like sparse networks from scratch, all these different papers on showing the effectiveness, and also OpenAI's research on sparse transformers to discuss how they're doing this in PyTorch and how it's making it easier to develop this and other things about moving into PyTorch. TensorFlow has published a blog post on hyperparameter tuning with the Keras Tuner API, describing using this automated hyperparameter search compared to manually searching something called grad student descent. So they discuss how you can use the Keras Tuner API. First, they show how to use it with this HyperResNet, which is part of the Keras Tuner applications, sort of like these like a predefined architecture in case you don't want to define your own architecture, and how you would interface that with the Keras Tuner hyperband, which is this like non-uniform resource allocation technique by doing this kind of an interface. So then the blog post goes on to show how you can search over your custom architectures. You do the, I'm assuming that they're importing the Keras Tuner as HP or something like that because of the way that the code is structured, but you see how you would define hp.in and then have this kind of a hyperparameter thing. So it's looking like when you do this kind of in range in Keras, basically what you're doing is as you loop through, you're doing the functional API to append the previous layer with by passing it in like this, like x equals, and then you pass in x, this kind of syntax. So basically the hyperparameter tuning is controlling the number of times that you loop through this, defining the number of convolutional blocks that are defined, as well as, the filters with this kind of syntax. So I think it, maybe a little messy, but this would be how you would do something like this, and definitely save you a ton of time by implementing something like hyperparameter tuning to get a better sense of different hyperparameters of your model. So at the end of doing this, with the hyperparameter algorithm, you can use this kind of API to get the best models from doing this, the best hyperparameter configurations. Then you also have the built-in HyperResNet, hyper-exception architectures for searching through different permutations of ResNets. And you can also do this with distributed training. So they discuss how you can either scale up with the distributed training API from Keras to do this by sending data to different workers or by sending different models to different workers and doing the automatic hyperparameter search on the different models simplified with this API. So the blog post goes through different ways of doing this, and definitely an interesting tool with respect to the Keras toolbelt. Another interesting update to AI this week was the release of Covariant.ai led by Peter Abil, this idea of bringing robots from the lab to the real world. So in their inaugural blog post, they discuss this idea of looking for ways to apply robotics and how they've settled on logistics and doing these kind of stock keeping units and doing this processing as the main function of the Covariant robots. So in the blog post, they discuss some of the challenges of this, things like how 3D cameras can't see through transparent objects like water bottles, and how they train their models in order to do this kind of a filtering with the transparent bottles with their vision systems, and then also describing their deployment in this company in Berlin, Germany, and how they're learning and improving how to do this kind of like sorting with the different objects that come through. So it's definitely a really interesting company that's doing really amazing things with robotics in the real world. Part 2 of TensorFlow's neural structured learning series on their YouTube channel has come out, describing this idea of training with graphs in addition to like classification to have this kind of a neighborhood loss as well as the classification loss. This video goes to describe document classification with respect to these citation graphs. So the idea here is that when you get a new document, you might want to classify it as, say, like what kind of paper it is. Is it natural language processing paper, computer vision, or maybe something that's more specific like compression, distillation, neural architecture search, something like that. So the idea would be that you have the document classification task. So you have the text features from the document. So the actual text that you do, tokenize, encode, that kind of system for doing the text classification. But in addition to that, in this example, you're going to use the citation neighbors to do this neural structured learning. So you're doing the document classification based on the text features, and then you're also structuring the loss with the nearest neighbors from the citation graph. So what papers are cited in the paper. So it's definitely an interesting problem to think about to frame your thinking of neural structured learning. So in this example, they show how you might do this. This is how you would load the graph data, this temp/graph.tsv with respect to the training data to have this kind of input into the model training. So then they show how you load the training data set, you define the model with the Keras, this is your base model. And then so what you do is you pass the base model into this system of configuring the graph for having the nearest neighbor's loss, and then how you go about training this to add the nearest neighbor's loss with respect to the other loss on the document classification with the text features. So definitely an interesting series showing how to do neural structured learning in TensorFlow. I also thought this blog post that came out on tokenizers, how machines read from Floyd Hub, is really interesting and worth checking out. It's a great overview of the ways in which text is processed into machine learning models. Starting off by just describing the idea of tokenization, this general idea of you take a sentence like "let's tokenize, isn't this easy?" and showing if you take tokenize on white spaces, you get this kind of an input compared to punctuation or having some kind of rules. So the blog post discusses all the different ways that have come out on tokenization, overview the literature going from subword tokenization to the byte pair encoding that's used in the Mina chatbot, unigram subword tokenization, word piece, and sentence piece. Definitely a great overview, a long read, but a great overview on tokenizers and natural language processing.